September 25, 2025, Harvard astronomers reviewing Atlas data noticed something impossible. The object is no longer on its predicted path. Within hours, NASA's Jet Propulsion Laboratory quietly updates its orbital solution, but with no public statement. Natural outgassing can push comets slightly, yet Atlas appears to have shifted by a margin too large for random physics. Internal notes mention non-gravitational impulses, stepwise accelerations, terms that belong to engineered craft, not icy fragments. The official line is silence. The evidence points to something else. Has Atlas broken the rules of nature, or has it just revealed it was never a comet at all? The first cracks in the story came not from government labs, but from open software. Bill Gray's orbital tracking code, used worldwide by both amateurs and professionals, began to show slight mismatches between prediction and reality. On September 23rd, those mismatches widened into a pattern. Atlas was running ahead of schedule, its sky position just far enough off that the software flagged a possible orbital solution error. The alert filtered to the Harvard-Smithsonian Center for Astrophysics, where analysts turned to fresh data from the Magellan telescopes in Chile. Their long baseline images confirmed the suspicion. Atlas was not where it should be. Its path had shifted by enough arcseconds to demand a formal update. At NASA's Jet Propulsion Laboratory, the Horizons database soon carried a new solution. The orbital parameters had been corrected, but the update appeared quietly, buried in the daily feed with no announcement. Those who watch such things noticed immediately. Ephemerides shared across amateur astronomy forums no longer lined up with older predictions. Telescopes pointed where Atlas should have been found, the sky empty. Then, with adjusted coordinates, the object appeared again, slightly brighter than expected, and clearly moving off its previous track. To the public, nothing unusual was said. The press releases never came. Inside Harvard, however, the phrasing of the internal bulletin was stark. Non-gravitational acceleration components observed. It was language that suggested not just cometary outgassing, but something more deliberate. For now, only those watching the fine print know what it means. The institutions remain quiet, yet the numbers tell the story. Atlas has shifted course, and no one can explain why. Comets can and do misbehave. Their surfaces crack, they vent streams of gas, and they tumble unpredictably. Astronomers have long documented small deviations, especially when sunlight hits volatile ices hidden beneath a crust. The effect is measurable but modest. A few arcseconds of drift here, a fractional change in timing there. Hubble archival studies of Halley's Comet and of Shoemaker-Levy 9 showed exactly this behavior. Tiny kicks, sometimes just meters per second, produced gradual offsets in the orbit. In every case, the shifts were predictable within a narrow range once the jets were accounted for. The nucleus, essentially an irregular snowball, behaved as physics dictates. Atlas has now broken that precedent. The September deviation projects to tens of thousands of kilometers in positional offset if extended over the coming weeks. That is not a subtle nudge. It is a redirection large enough to alter where the comet will be when it passes perihelion. Analysts attempting to fit the curve report stepwise changes, not the smooth acceleration one expects from solar heating. The orbit bends, then straightens, as though pushed in discrete pulses. The odds of spontaneous venting producing such a clean profile are vanishingly small. Even the most optimistic natural models strain under the numbers. To reach this scale requires outgassing far beyond what Atlas has shown in any spectrum to date, which leaves a troubling bridge. If the forces are not smooth, and if the energy required exceeds natural limits, then the hypothesis of controlled thrusts emerges. Official reports avoid the term, preferring non-gravitational impulse. Yet between the lines, the meaning is clear. This is not how comets move. Unless physics has written a new exception, Atlas may be under guidance. The timing compounds the mystery. Atlas is racing toward perihelion on October 17th, a trajectory that already threads dangerously close to the sun's glare. The new deviation bends its track even deeper into that corridor, where ground-based telescopes will lose all visibility. From October 8th through October 18th, the solar conjunction blackout takes hold. During that period, Earth-based observatories cannot safely point instruments into the glare. Even space telescopes must limit exposures to protect sensitive sensors. The result is a 10-day gap, exactly overlapping the moment when Atlas will pass closest to the Sun and when its course change will matter most. NASA and Harvard analysts are racing to refine models before the blackout begins. Each night, new fits are distributed, each one diverging further from the last. The ephemerides now carry caveats, positional uncertainties expanding by the hour. A comet that was once just a curiosity now defies prediction. The stakes are obvious. If Atlas is maneuvering, its most decisive action could take place entirely out of view. The Sun itself becomes a shield, hiding whatever occurs at perihelion. When it reemerges, days later, its trajectory may reveal whether the shift was natural or deliberate. As one analyst put it off the record, "We may not see what Atlas does until it is too late." The blackout window has turned a simple orbital anomaly into a corridor of complete uncertainty. And within that window, anything could happen. Inside Harvard's Center for Astrophysics, the first formal language about Atlas's anomaly appeared in a draft memo circulated among orbital dynamics staff. The document, never intended for the public, described stepwise acceleration events inconsistent with random outgassing. In academic terms, that phrasing is extraordinary. Comet reports normally speak of sublimation rates or jet models. Here, the bullet point sounded more like a spacecraft diagnostic. The most striking line came near the conclusion, "Engineered impulse, not excluded." For cautious scientists, those words are as close as anyone will come to admitting the unthinkable. Meanwhile, at NASA's Jet Propulsion Laboratory, the response was far quieter. Horizon's database entries were corrected daily. Orbital solutions were nudged, but no press release followed. No briefing was held. To anyone not watching closely, Atlas looked like just another routine comet update. The contrast could not be sharper. In Cambridge, private notes whisper of engineered impulses. In Pasadena, the silence is total. Analysts at both institutions are seeing the same data, but their handling of it reflects different instincts. Harvard's drafts let the possibility slip into writing, while NASA's edits bury the change in code. This tension raises a deeper question. If Atlas is maneuvering, what is the purpose of showing that maneuver now? Is it a signal meant to be noticed? Or is it simply the unavoidable trace of a course correction in progress? To change the path of an interstellar object is no small feat. Even a deflection of a fraction of a degree requires enormous energy. Calculations based on Atlas's estimated mass suggest that a 0.1 degree deviation corresponds to a delta VI impulse in the tens of meters per second. For a nucleus tens to hundreds of meters across, that translates to gigawatts of sustained power. The numbers align uncomfortably well with earlier anomalies. In July and August, Atlas appeared to fire 3 discrete thrust pulses. Each event produced an acceleration equivalent to about 10 gigawatts of energy release, roughly equal to the combined output of 10 large nuclear power plants. If the September course change represents a similar impulse, then the comet is not drifting. It is steering. Mainstream scientists frame this as a debate between two models. The first is the thermal heartbeat scenario, in which buried pockets of volatile ices rupture in sequence, producing short, powerful jets. The second is the engineered pulse hypothesis, in which the accelerations are deliberate, the result of an internal power source. The former stretches known physics, but remains possible. The latter ventures into speculation, but explains the clean, stepwise pattern more directly. The bridge to Swan is telling. Swan, discovered just days earlier, shows immense stability, a fortress-like body whose orbit remains steady even under solar stress. Atlas, by contrast, behaves like an agile probe, adjusting its trajectory in visible increments. Together, they resemble complementary roles: one tank, one scout, one stable, one maneuverable. If the energy estimates hold, then Atlas has demonstrated a controlled burn on interstellar scales. Whether natural or engineered, the fact remains. The physics point to power on a level we should not be seeing from a comet. Theories about Atlas's behavior now cluster around 3 speculative mission profiles. None are proven, but each matches elements of the data. The first is the Scout probe hypothesis. In this frame, Atlas is the agile pathfinder, steering actively toward a rendezvous. Its stepwise course changes resemble navigation corrections, the kind performed by spacecraft as they approach targets. The second is the correction burn scenario. If Atlas had drifted from its intended line, the September deflection could represent a correction maneuver, nudging it back into a precise corridor near the Sun. Such adjustments are routine in human mission planning and would explain the timing just weeks before perihelion. The third is the decoy or test unit hypothesis. Here, Atlas is not the main event, but a distraction. Its conspicuous maneuvers draw observation and speculation, while another objective unfolds elsewhere. Alternatively, Atlas may serve as a test, probing our detection networks to see how quickly we notice, how we respond, and whether we can track a maneuvering body at all. Harvard and NASA data cannot prove any of these scenarios. Officially, each remains speculation. Yet the pattern of thrust-like impulses, the gigawatt energy estimates, and the silence from major agencies align more closely with mission profiles than with random cometary venting, which leads to the most unsettling question so far. Is Atlas steering itself through internal systems, or is it being steered remotely from somewhere else? As the blackout window approaches, strange restrictions ripple through the astronomy community. Rumors circulate of telescope allocations quietly withdrawn, observing runs postponed, and proposals denied without explanation. Instruments that would normally capture comets at perihelion are reassigned to other targets. At Harvard, researchers whisper about unusual instructions. Drafts of papers describing Atlas's non-gravitational accelerations are held back, with internal emails suggesting publication should wait until after the blackout has passed. The caution is framed as peer-review discipline, but the timing raises questions. NASA, for its part, speaks carefully in public. Official statements emphasize natural processes, citing outgassing as the expected cause of orbital deviations. Yet behind the scenes, JPL analysts are recalculating Atlas's orbit daily, updating horizons with new fits that shift subtly with each iteration. The very act of constant correction betrays the uncertainty. The silence itself becomes a signal. If nothing unusual is happening, why the clampdown? If Atlas is just another comet, why the hesitation to publish what should be routine updates? For those watching closely, the absence of information is as loud as any press conference, which leaves the observers outside the system. If the agencies step back, then the burden of truth falls to the distributed networks that cannot be silenced. Into the vacuum left by official channels steps a familiar figure. Bill Gray, long known for his open-source orbit solutions, begins rallying a network of backyard astronomers and small observatories under the banner Atlas Watch 2025. His message spreads across forums and encrypted channels. Do not wait for official data. Gather your own. Before October 8th, wide-field imaging remains the best tool. Even modest telescopes can capture Atlas's motion against background stars, and time-stamped images contribute to trajectory fits that rival professional networks. For those without optics, radio amateurs test creative approaches. Some experiment with backscatter detection, bouncing signals off the comet's expanding coma. Others attempt occultation timings, measuring the moments when Atlas crosses in front of faint stars to trace its profile. The goal is simple. If Atlas is changing course, every data point matters. 1,000 small observations can reveal what one giant telescope cannot. In this moment, the grassroots become the only line of continuity through the blackout. The call to action is clear. If you have a scope, use it. If you have a dish, point it. If you can time or track, log everything. Raw data must come from everywhere, not just from locked-down labs. Because once the blackout begins, the only way to know what Atlas is doing will be to watch for yourself. The story of 3I Atlas is no longer about routine orbital mechanics. A comet expected to follow physics has defied its predictions. Harvard's Center for Astrophysics confirmed the anomaly, and NASA's Jet Propulsion Laboratory updated its solutions in silence. The numbers point to stepwise accelerations. The energy estimates point to gigawatt-scale power. For a passive fragment of ice and rock, such forces should be impossible. The blackout window ensures that the crucial days of perihelion will unfold unseen. Between October 8th and 18th, when Atlas comes closest to the Sun, ground-based telescopes will be blind. Agencies are recalculating daily, But no one will know the truth until it emerges from glare. Speculation has already filled the gap. Is Atlas a scout probe adjusting its path? A malfunctioning unit correcting its orbit? A decoy drawing our eyes while something else passes unnoticed? Or is it still, despite everything, an icy comet with natural physics stretched to their limits? The stakes rise with every unanswered question. If Atlas re-emerges shattered, the anomaly may end as just another cosmic curiosity. But if it re-emerges intact, with a trajectory that defies chance, the implications are staggering. When the sun releases Atlas back into view, we will face the answer. A frozen relic of the interstellar void, or a controlled craft demonstrating its presence. The blackout leaves us waiting. Subscribe and stay with us, because the moment the first post-blackout images appear, we will break them down here. Swan and Atlas are rewriting the rules of the solar system, and when they return to sight, the story may change forever.